Imagine if gravity wasn't the curvature of space-time. Imagine it was nothing more than a force, exactly as Newton described, a pull between masses with no connection to the fabric of space and time. If gravity were only a force, would light still bend near stars? Would planetary orbits remain stable the way we know them? Would time itself stay perfectly uniform, untouched by motion or mass? And would we ever understand the Big Bang, the expansion of the universe, or black holes the way we do today? In this video, we step into an alternate timeline, a universe where general relativity was never born and gravity never changed its identity since Newton. In this alternate world, gravity is simply Newton's force, a mutual attraction acting between masses, instantaneous in effect in the classic model, and completely independent of the structure of space and time. Phenomena like Mercury's anomalous orbit would remain unexplained, resistant deviations with no theoretical framework capable of resolving them accurately. In the movie of Interstellar, gravity shapes the orbits and extreme trajectories near massive objects like Gargantua. In a purely Newtonian universe, these trajectories would be far simpler and less dramatic. No space-time curvature to warp motion. Without general relativity, the idea that space and time are a unified, dynamic entity, a deformable space-time, simply doesn't exist. Light wouldn't follow curved geodesics, because in this universe, there is no fabric to bend. Thus, gravitational lensing would either look fundamentally different or might never be predicted at all. Gravitational waves? Impossible! They are ripples in space-time itself, and without curved space-time, the concept disappears. In the movie, light curves dramatically around the black hole Gargantua. Without relativity, light would travel straight, no bending, and the cosmos would appear very different.
Time is relative, okay? It can stretch and it can squeeze, but it can't run backwards. It just can't. The only thing that can move across dimensions like time is gravity. Gravity on that planet will slow our clock compared to Earth's drastically.
I bet. Well, every hour we spend on that planet will be 7 years back on Earth.
Time as an untouchable constant. Gravitational time dilation doesn't occur. A clock on Earth's surface would tick at the same rate as a clock far above the planet. No slowing down due to deeper gravitational potential. GPS systems would fail without relativistic corrections. Modern experiments measuring time dilation over mere centimeters of height would produce no effect.
The waves.
Oh shit.
That was moving away from us.
We need the recorder.
Brand Doyle, back to the Ranger now.
We're not leaving without her data.
Get back here now. We do not have time. The second wave is coming. We're in the middle of a swell.
I got it.
Get your ass back to the Ranger now. Brand, get back here now.
Go. I can't make it. Go.
The famous scene where 1 hour on a planet, Miller, near a black hole equals 7 years on Earth would be impossible. In a Newtonian only universe, time flows uniformly everywhere. Are you ready to know what happens to black holes and singularities? Without Einstein's equations, black holes, as we understand them, wouldn't exist. No space-time singularities, no event horizons. Collapsing stars would follow simpler Newtonian dynamics, without the dramatic consequences predicted by relativity. The depiction of Gargantua's accretion disk and warped space-time shows what relativistic physics predicts. Without general relativity, these effects vanish, and black holes would be far less exotic. Cosmology in a pre-relativistic world. The Big Bang cosmic expansion and the structure of the universe fundamentally depend on general relativity. Without it, the expansion of the universe might never be discovered or understood. Galaxy dynamics and large-scale structures would be misinterpreted or remain unexplained. Our mathematical framework for cosmic evolution would be far weaker. The movie illustrates extreme cosmological scenarios, black holes, wormholes, and time dilation effects, all grounded in relativity. Without it, our universe would be visually and physically less dramatic. And the alternative theories of gravity. Scientists in a Newtonian-only world would likely develop alternative gravity models to explain anomalies. Scalar fields, vector fields, or hybrid models might appear, but no theory would match the precision and predictive power of general relativity in explaining orbits, light paths, or cosmological dynamics. Finally, the quantum world without relativity. One of modern physics' biggest challenges is unifying quantum mechanics with general relativity. In a universe without relativity, this tension might disappear, but we would lose our ability to describe gravity at macroscopic scales. No concept of curved spacetime at quantum distances, leaving quantum gravity entirely speculative. So, before we end this journey, let me leave you with 2 questions. Questions that reveal how you choose to understand the universe itself. First, if general relativity had never existed, if space-time never curved, if light never bent, if time never stretched or slowed, what kind of universe do you think we would be living in today? A simpler one? A poorer one? Or a universe fundamentally incomplete? And second, on a personal level, which universe would you rather inhabit? Newton's universe, where gravity is just a force pulling on masses, classical, mechanical, predictable? Or Einstein universe, where gravity sculpts space-time, where clocks stretch and collapse, where black holes spin like engines, and where time itself becomes a flexible dimension? As for me, I choose Einstein's universe, because that's the universe where the real challenge lives. The search for a unified theory, one equation that finally brings general relativity and quantum mechanics together. That quest doesn't even exist in Newton's universe, but it defines mine. So tell me, which universe do you choose and why?